Right, good morning everyone. So we were discussing PAC learning in our last class. So friends, today we will talk about PAC learning and followed by VC dimension. So they come under computational learning theory, right? So first of all, let me show you what is computational. What do we mean by computational learning theory? Then PAC learning anyhow we have discussed in the last class. We will try to complete that today, right? Fine. So I have shared my screen. So show you. So in the last class, we have done this program. In the last lab, we have done this program, database connectivity program. We have seen the output also, right? Procedure was explained completely. So I expect the students to implement database connectivity from Python and also submit the same thing as part of your lab experiment, right? So your lab marks will be evaluated purely based on your submissions, my dear. There is no doubt in that. So fine. So today what we will be discussing is under computational learning theory. There are two topics. One is called as PAC learning. Another one is called as VC dimension. Right. So both we will be discussing today. Hopefully both we can complete. PAC learning already we have started. So but we need to have little basics of computational learning theory, right? So what is computational learning theory and what exactly we mean by computational learning theory, right? So coming to this one, right? So friends, please observe computational learning theory. This itself is a separate subject, my dear friends, right? So computational learning theory itself is a separate subject, right? And what is the use of computational learning theory in our machine learning course? That is what is the point, right? So what general laws constrain the inductive learning? So if you remember right from the beginning, we were using the word concept learning or inductive learning, right? Inductive learning means a machine learning model will try to learn from some training examples, and then it will try to predict or it will try to work on the unseen data, unobserved data, or test data, right? So we have a very small sample of training data with which we will train our machine learning model, and machine learning model will further work on the new data, right? Like we have seen examples of height and weights, right? We train our model by giving some set of heights and weights, and our model will predict for a given height what should be the weight. So that example we have seen. We have seen playing tennis example in decision trees and candidate elimination algorithm. Like that, we have seen couple of examples, 3 to 4 different examples in our respective topics like linear regression. Then we have seen find S algorithm, candidate elimination, decision tree, and even naive-Bayes classifier. So what is the role of computational theory is, till now whatever machine learning models we have seen, right? Y equal to mx plus c is a linear regression model which we have seen height weight example. Then find S algorithm is again for concept learning or inductive learning, and candidate elimination algorithm is something which is, you can say, better than find S algorithm. It gives you more number of possible hypotheses as the output. And then we have seen decision trees, right? After that we have also seen naive-Bayes classification, which is based on Bayes theorem, right? So these many machine learning models we have seen, right? And if you observe, all of them are based on inductive learning only. So what is inductive learning? Inductive learning means we give a small training data, small sample data, right? And we want our machine learning model to apply some sort of mathematical function, right? To study the relationship between the outputs and inputs, which we call it as hypothesis, right? Or the target function. So this target function or the hypothesis is derived by our machine learning models, and these hypothesis functions or target functions will be applied on the new data, and that is how a machine learning model is generally created, right? So in this we have variety of inductive learning examples which we have seen till now, as I have mentioned the list, right from regression model to naive-based classifier. So in inductive learning, there are certain points to be observed, certain questions need to be answered, right? Some of them are listed out in this particular slide, and to answer these important points or to answer these questions, we take the help of computational learning theory. So, friends, what is the reason for using computational learning theory in machine learning? Means there are certain things in inductive learning for which we need answers. For example, number of training examples, right? Suppose I have given 14 examples. We have 14 training records we have seen in our playing tennis example. So 14 are enough, or shall I go for 140 examples? What should be the size of training data? 10 records, 20 records, 100 records, or 1 lakh records, or 10 lakh records? So, what is the ideal size of training data? Right? What should be the minimum size of training data? What happens if we have excessive training data? Means if you have too much training data, heavy size of training data, if the training data is too large, again, is it going to create any problem? So what will be the ideal size of training examples that we would like to know? And what is the probability of success of our machine learning model? Suppose if we developed a machine learning model which is also called as a learner, right? So what we want to know is what is the probability of successful learning, right? So if I give some tested data, what is the probability that my machine learning model or my hypothesis is working properly, right? If at all I have multiple hypotheses for the same problem, in that case, which hypothesis offers me the best possible result, or the best hypothesis which offers me minimum errors? So how do I find all these things? How do I find the probability of successful learning? What should be the number of training examples? And what is the complexity of the hypothesis, right? And accuracy to which the target concept is approximated, right? Manner in which training examples are presented. Means the training examples which we got, it is very, very important that these training examples need to be correct. Otherwise, the hypothesis generated will be incorrect. And of course, the predictions made by that hypothesis, or the calculations made by that hypothesis, or the decisions made by that hypothesis will also be incorrect, right? So to answer these particular important issues, we seek the support of computational learning theory. And under computational learning theory only, we will get these two important topics. One is PAC learning probability, probably approximately correct. Probably approximately correct. So under computational theory, we will be discussing these two important techniques. One is called as PAC, another one is called as VC dimension, right? Another one is called as VC, right? So friends, quickly, can anyone tell me why the accuracy of our machine learning models is not 100%? Right, why it is not 100%? Why always we say that I am trying for better accuracy, right? Why it will not be 100%? Can anybody guess? Any guesses? You can respond in the chat box. Why these machine learning models don't offer you 100% accuracy? Any guesses? 588, A3, B5, M0, D5, 515, H0, 514, 572. Nobody can guess. insufficient training, right? That's true. It is because of insufficient training, right? Any other answer? So maybe the training data itself is not enough. Insufficient training can be one reason. Another important reason is the training examples, the samples which we have given for our machine learning model. To what extent this sample data is correct? That is also important. Correctness of the training data is also important, right? So always what we do is we will only give some sample data to our machine learning model, right? So friends, for example, if I want to develop a machine learning model to predict whether a given image contains a cat or not, then what should I do? First of all, I should train my machine learning model by giving or by showing different types of cat images to my model. Right? How many cats I will use in my training model? 100,000, 10,000, 20,000, maybe 1 lakh, right? I can't go beyond that, right? 1 lakh, 2 lakh images. From where do I get? Right, even if I get them also, how do I train? My computational requirements will also be very high. Of course, we have a lot of GPUs available today. Computational requirements are not a big problem today because of the availability of advanced GPU based hardware. So computation is not a big deal, but still, from where do you get sample data of 1 lakh images, 2 lakh images, right? So obviously the sample data which we are giving is very less. That's the reason we can't really expect 100% accuracy, right? And what we do is we will try to improve. Initially, whatever hypothesis is generated, we will see how much accuracy it is giving, and accordingly we try to improve that accuracy by making some necessary changes in the model, or by increasing the training data, or by making some corrections in the training data also. Sometimes there can be errors in the training data, right? Now coming back to our computational learning theory. So under computational learning theory, there are two important techniques. One is called as PAC, probably approximately correct learning. Another one is called as VC dimension, right? So what is the purpose of probably approximately correct learning, right? That we have started discussing this fact yesterday. So let me write it here. What is the purpose of this one is, suppose you have an hypothesis. Suppose we have a hypothesis called as small h, right? So I have h1, h2, h3, like that. I can have multiple hypotheses which belong. I call this one as h1. H belongs to capital H, right? So what we need is, among h1, h2, h3, h4, which hypothesis offers me better accuracy I would like to find. Right? So that's the reason we use PAC learning to identify or to select the most accurate hypothesis, right? And VC dimension, its purpose is different, right? VC dimension is used to find the capability or capacity of a classifier, of a specifically binary classifier, right? So suppose you have got problem in hand and you want to do a classification problem. You want to solve a classification problem. VC dimension will tell you which classifier should be used, right? Which classification mechanism can be used, or for a given classifier, what is the capacity of that classifier. To identify or to find, to calculate the capacity of a classifier, we use VC dimension. So we will come back to VC dimension. Before that, we will complete PAC learning, which we have discussed in our previous class, right? So we have seen this. So let me erase this one. So please observe this carefully, my dear students. Right. Let us assume this is MSET rank. In the last class also we have used similar example, and let us assume this is intermediate marks. inter marks, 10 plus 2, right? Now there are certain points like plus, 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 and let us have some negative points, minus, 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 right? So friends, please observe here, please observe that, so let us assume that this plus represents that it's a positive example. So positive example means this is minus here. So positive example means based on the MSET rank and intermediate marks, a student may get a seat in our college. Negative example means based on this particular rank and so and so intermediate marks, a student may not get a seat in our college, right? So let me try to represent this one. Let me try to represent this with a particular box. I'll say all the students who may get seat in our college, right? This is the range. This is the range. This is square or rectangle, whatever you call it as. So this box, pink color box, represents all positive examples. Means let us assume this is our target, our original expected one. This is the fact, this is true. Like, let me represent this one with C. Means if a student is supposed to get a seat in our college, then he should have certain MSET rank and some amount of intermediate marks. That combination represents either he will get a seat or not. So negative means he will not get the seat, positive means he got the seat. Now what I have done is, as I told you, I cannot build a hypothesis which is 100% accurate. Please try to understand, I cannot build a hypothesis which is 100% accurate. This C which you are seeing on the screen, the one which is represented with pink color, that is actually showing the ideal hypothesis. Ideal hypothesis. Ideal hypothesis means the hypothesis which will give me 100% accuracy. Right, like that it should identify like this box contains all positive examples, anything outside the box is a negative example, right? But the problem is, what I will do, I will train my machine learning model by giving some last year data or before last year data, and I try to train my machine learning model and I try to generate a hypothesis, and that machine learning model or that hypothesis will make some predictions, right? Now obviously the hypothesis which we are going to generate will not be 100% accurate. So please observe, my dear friends, please observe here, observe carefully. Suppose, just imagine this one, the hypothesis which I have generated, let me call this one as H, right? So it is very, very clear that as per my hypothesis, if you observe the hypothesis which I have generated or my machine learning model, what this machine learning model is doing is, see here, out of 4 positive examples, only 2 are covered. Remaining 2 are not covered in my hypothesis. Means as per my hypothesis, these 2 positive examples are also considered to be negative. And my hypothesis is considering these 4 negative examples which are in this green box, and it is treating them as positive, right? So please observe that C is our expected one, C is our expected ideal function, right? C is our expected ideal function, but H is the hypothesis which we have generated, and C is not exactly same as H, right? So now what I'm trying to do is I'll try to represent the same concept with a simple diagram, right? Same thing, I'm just redrawing it. So this is my C, and this is my H. This is H, and this is C. So friends, if you observe the area or the portion in which C and H are overlapping, right, it means that this is the place where my hypothesis is correct. My hypothesis is correct in only in this particular region overlapped. C is expected answer, H is generated answer. It's like that. So my hypothesis is matching with C only in this particular overlapped region, means here this part. These 2 plus examples which you are seeing on the left side, right, this part is the overlapped region, right? So beside this one, means apart from this overlapped region, right, whatever is there, right, so this part is my error. Now hypothesis is not fully matching. If there is no error, means it should come something like this. No error means I should get my C like this, and my H should also be same as C. Then we say this is totally correct, but it is never possible, sir. It is not at all possible. It is not at all possible. So you have understood, like, yes, our H will not be equal to C, that we know very well. Now what we need to understand, or what we need to do with PAC learning is, right, now friends, point number one. Point number one, please observe here. Point number one. Yeah. Sample error. What is sample error? We have like 14 records training data. In those training records, when I apply my hypothesis, out of my sample records, 14 records, 9 were yes, 5 were no, if you recollect playing tennis example. So in the sample data, for this sample data, how many times my hypothesis worked successfully, in how many sample records it failed. That is sample error. You know that. Now another word is there which is called as true error. These words we have discussed in our previous classes. True error means the total data set, on my entire data set, when I applied this hypothesis, how many times it was working successfully, in how many cases it failed. So this one, this particular HC not equal to H, this is our true error, sir. This is our true error. This is our true error, right? This will be done on the entire data set, capital D. So if I have 1 lakh records, on my 1 lakh records, when I apply the hypothesis, what were the expected answers, what were the generated answers, right? So that is called as true error. Now what we expect from PAC learning, or what PAC learning says is, this is important, what PAC learning says is, what PAC learning says is, yeah, this true error, whatever we have, this, what is true error, now we know, right? So this true error, or the error which you have seen, must be, true error must be less than epsilon, right? and epsilon value is 0 is less than epsilon, and epsilon is less than 1 by 2, means 0.5. So the range of epsilon is 0 to 0.5. So the number of errors, the error which an hypothesis can commit, or the range of that error must be somewhere less than 0.5. It should be less than epsilon. Epsilon's range is 0 to zero point 0.5, right? So the probability, so friends, if you observe, I can represent this one with a mathematical equation P of C XOR. Why XOR operation? This region is C XOR H, right? The area which is covered by C, not covered by H. Similarly, the area which is covered by H, not covered by C. So this region, right? This region, see here, this particular region, this part and this part. So this region is our error, right? This region is our error. So this region is our error. That error portion or error region is represented by C XOR H. So probability of C XOR H must be less than or equal to epsilon. This is what is PAC learning says, right? And the probability, right, of course the number of errors must be less than or equal to epsilon, and there is one more important quantity which is called as delta, right? So the number of errors or the probability or the failure rate, of a hypothesis can be represented with delta. The failure rate, the probability of failure must be equal to delta. Probability of the failure must be equal to delta. It means that the probability of successful learning, SL, probability of successful learning must be equal to 1 minus delta. So probability of failure is given with delta. If probability of failure is delta, then the probability of successful learning must be 1 minus delta. Probability of successful learning will be 1 minus delta, right? So to complete this, so what is a true error we know, and what do you mean by probably approximately correct hypothesis? An hypothesis is said to be probably approximately correct hypothesis if the error rate is less than epsilon, or it is in the range of that epsilon, and the failure rate must be less than delta. Failure rate should be less than or equal to delta. So let us try to take another simple example so that we understand PAC in detail, right? So please observe this carefully. So let me erase this one, clear screen. Let us take an example. Right. So friends, please observe here. Suppose I have a hypothesis. For example, I have a hypothesis H1. Now, in the problem, on PAC learning also you can expect the problem, friends. So what is the epsilon? What is the epsilon? Its range is 0 to 0.5, 0 to 0.5. Suppose epsilon's range was given as 0.05. In the problem, they will give you the range of epsilon. Then delta. Delta is equal to 0.2, 0.20, something like this. Now friends, this is a hypothesis H1. So if you remember our heights and weights example, even though we applied the formula of m slope slope formula as well as intercept formula, when we have calculated y equal to mx plus c values, we got lot of difference, right? Like expected value and generated values were not same, and we got the difference also, if you try to recollect that example. So those differences are written here. So for example, 1 2 3 4 5 6 7 8 9 10. So friends, for example, this cell represents the difference between expected answer and generated answer. Let us say the difference between expected and generated answer on the first record is 0.001, and on the second record, oh, it's not, we make it number, right? So just imagine this is 0.001. Let me make a small second. Right. So in second case, let us assume it is 0.06. In third case, it is 0.001. 0.06, 0.01, 0.01, 0.02. Right. So if you observe these 10 examples, friends, these 10 are 10 sample records. On these 10 sample records, I applied my hypothesis. I know what is the expected value because this is training data, right? So I got some generated value when I applied H1. So the difference between expected data and generated data, that the difference I have written. Now, what do you mean by PAC learning is, please observe here. In first record, what is the value? 0.001. Is it less than this error or not? Less than epsilon value 0.05 is the epsilon value given to you. So for the given epsilon value, the first records what we say error is less than epsilon. So this is okay for me. This is fine. I don't have any problem. But if you observe second one, 0.06 for second record, the margin of error is greater than epsilon. For second record, the margin of error is greater than epsilon. Similarly, for seventh record, the margin of error is greater than epsilon. So what we have to do is, friends, here, how many total records I have? I have total 10 records. In those 10 records, how many times, in how many records the error rate was less than the given epsilon value? In 8 cases, it was less than epsilon only. Only second record and seventh record, the error was, difference was greater than the accepted error or accepted difference. So 8 times it was satisfying my epsilon value. So you can say the percentage is 80%, right? Or you can say simply you can write it as, right, 0.8. Fine. Now if I subtract this 1 from 1 minus 0.8, this is coming to 0.2, right? It means the success rate of this particular hypothesis H1, success rate of H1 is equal to the delta which we have given, 0.2. So H1 can be accepted. That is the point. H1 can be accepted. Friends, for example, I have another hypothesis. Let us say H2. H2. And in this H2, let us assume there are 0.06, 0.076, somewhere here 0.07. Let us say in second hypothesis, out of 10, 3 cases there is the difference was going beyond the epsilon. So here the success rate is 70%, and if I subtract 1 minus zero point 0.7, I'll get 0.3. So for H2, for H2, H2, what is happening is I am getting 0.3. This 0.3 is greater than delta. 0.3 is greater than delta. So second hypothesis H2, oh, this is H2, right? Second hypothesis H2 cannot be accepted, or you can say second hypothesis H2 should not be selected. So when you have multiple hypotheses, if you want to know which hypothesis is more accurate, then you are going to apply this PAC learning. Now I can say H1 is probably approximately correct. Probably approximately correct. That is called as PAC, right? So this is what is PAC learning, my dear friends. So mostly you may expect a theory question in your exam, but a problem can be given. If a problem is given, very simple, they have to give epsilon value and delta value in the question, and they expect you to identify, for given 2 or 3 hypotheses, you need to identify which one is most probably approximately correct hypothesis, right? So is it clear? PAC hypothesis, PAC learning is clear to everyone? Please respond in the chat box immediately. Yes, please respond in the chat box. Yes, that's great. So now we will move on to VC dimension, right? What is the purpose of VC dimension? VC dimension, let me show you, right? So friends, in the definitions which you see, you will find some complicated words or complicated math related statements. So you should not be worrying about that. So that if the definition contains a lot of symbols, we will write those symbols in the answer. But we try to understand them by taking examples, the way we have solved Naive-Bayes classifier algorithm, or the way we have discussed PAC learning. For everything, we will try to take up a simple example. We will try to make the concepts very clear. Then we will move on to the next concept, right? So the VC dimension measures the capacity of a binary classifier. The VC dimension is defined as being the largest possible value of M for which there exists training data, right, of M different points, different X points that classifier can label arbitrarily, right? So what do you mean by this? What do you mean by this? What should I understand by this VC dimension, right? So let us try to understand this one. Right. VC stands for Vapnik-Chervonik's dimension. It's the name of the person who has actually designed it. So what we are going to do in VC dimension is we are going to shatter means we are going to spread across our hypothesis. We are going to shatter our hypothesis, right? Such that, right, H shatters N. All the data points, we will try to shatter the data points such that we will try to see is there any hypothesis which belongs to hypothesis space. Capital H means hypothesis space, right? So what we want to do is n points can be labeled with 2 power n ways. as positive and negative. N points can be labeled in 2 power n ways as positive and negative, and we will try to see, right, how well we can classify them using VC dimension. Means whether I should go for a line classifier or whether I should go for naive based classifier. Shall I go for a multi-layered perceptron? So what kind of classifier should I use? That I will come to know by using VC dimension. This definition which you are seeing on the screen is little complicated. You may not understand it, but no issue. We will try to take a very small example and we try to understand this one, right? So please observe this carefully. Please observe this carefully. For example, I have two data points. Here n is 2. So I have two data points. With two data points, how many combinations I'll get? With two data points, how many combinations I'll get? With two data points, I'll get 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. With two data points, I get 4 combinations, right? So suppose if I want to represent them, like I can call it as 0, 0 is one combination, 0, 1 is one combination, 1, 1 is 1, 0 is another combination, 1, 1 is another combination, right? So what I'll do is, now I need to classify them. I need to classify them such that all positive examples should come to one side, all negative examples should come to another side, right? We will see how well I can do it. See here. Observe this carefully. Now I have two data points, right? So one data point I will represent with what I'll do is, one data point I'll represent with green color, another data point I will represent with pink color or red, whatever it is. So how many combinations I'll get? One green, one pink, right? Another combination, so this one is pink and this one is green. Another combination, both are green. Another combination, both are pink, right? So now my point is, can I classify them with a simple line, right? So friends, here there are 2 points. One I am representing with pink, another I am representing with green. So the one which I am representing with pink, let us assume that is positive example. The one which I am representing with green, let us assume it is negative example. So friends, simply by drawing a line, we will wind up in another 1 minute. Simply by drawing a line, I can classify. See, everything which is on the left side is positive, everything which is on the right side is negative. I can easily classify with a line. Similarly here, I can draw a line here and I can say all pink are positive, and that's the reason they are on one side of the line, and the other side of the line will be negative. Similarly, I can say a line is drawn like this, and I can say anything beside this line is positive, anything right side of this line is negative. Similarly, I can draw a line here. I can say green is negative, pink is positive. So if you observe carefully, with a line, I can classify two data points. If I have n value as 2, if my data points are 2, I can classify them with a line, right? A line basically represents a regression problem, right? Height weight example, where you have only one dependent variable, one independent variable, linear regression, right? So friends, what is the purpose of VC dimension? Means VC dimension, what we try to do in VC dimension is, we will try to identify how many points are there and how do I classify them. So suppose here I'll come to know that if there are 2 points, a line classifier is enough. A line classifier is enough if you are dealing with 2 data points. Line classifier means regression, linear regression is enough to solve if there are 2 data points. You need not go for naive Bayes classifier, you need not go for a decision tree, you need not go for a complex neural network. So what type of classifier I should choose, what type of classifier I should use, that will be decided, or that can be the capacity of the classifier can be estimated using VC dimension, right? So I hope till this point it is clear. We will take another example of 3 data points, 4 data points, right? We will try to understand how VC dimension can help us in deciding what is the capacity of a classifier and which classifier should I use for a given problem, right? So I hope things are clear till this point. Please respond in the chat box and we will continue in our next class. So kindly respond in the chat box. PC, PAC learning and VC dimension are clear to everyone. Please respond. Yeah, that's great. That's great. So thank you one and all. We'll meet in the next class.